So record. All right. Good morning, everyone. And this week will be a trial week, just like what I said last time. And we're still going to be going over our discussion uh, like a normal day, but with a few adjustments. We're not really that impacted because, oh, hi, Nash, because we have
Yeah, I
modules.
can hear him.
Good morning. I'm
Good
recording
morning.
this so people can watch this later. So we're not really highly impacted because we have modules. Most of your grades, apart from exams, are about half of it are from modules anyway. So it's gonna be easier for us to adjust to the changes. The only thing that will be affected would be the handbook, which we will turn into another type of resource. I'm still thinking of how we could navigate on that. But for now, I have an online version of the PowerPoint. It's no longer the same type of PowerPoint. I edited this already. Uh, we'll probably cover the main thing as a group. So, and then I'll just assign you straight to the modules for reading and some of those checkpoints or quizzes. So we won't technically be using the whole 2 hour period, but I can stay online the whole time if you have some questions. Does that make sense? So we're just going to be going over the discussion part, and then our breakout session, our group work will become like individual. uh, this is the thing we'll be trying as of the moment and see if it works out or not. Okay, so we have for today we have actually moved to module 12. We kind of crept into the first part of module 12 last time, but that weren't able to progress. So um, uh, ignore the agenda. Agenda seems to be not updated. Okay, so um, we're going to be reviewing a few things. There's going to be some changes because now, always, sometimes, never is now going to be part of our discussion as part of the review. And we'll kind of like look at what we have, this word here, the underlining, the normal distributions. We haven't heard that word before. We haven't talked about that yet. And we'll know about it right now. So thing that you need to know is it's a kind of a distribution. Okay. And as you know, distributions are like a summary, like a visual summary, or sometimes a table, a visual summary of our data. Okay, so let's go on some of the major announcements as far as discussion boards are concerned. Um, I'm assigning module 10. We're behind that. That's due on the date that is listed there. Just I need to minimize this. Okay, there you go. All right. So due March 22. We will suspend the packet check for now, and probably just do that when we come back. Don't forget to post on discussion boards and to provide to high quality feedback. Class is great in doing that so far, so I don't have any issues as far as that is concerned. Um, now, to finalize your scores and everything, the closing date, I moved the closing date of modules 4 to 10 of discussion boards to March 31. So just so you know, that's going to be the new deadline for 4 to 10. So I can just finalize the grades. If you haven't taken up the group quiz, let me know. And make sure you're also current with the checkpoints as well. This is the best time to be current with the checkpoint because we have a lot of time at home. um, so make sure you are current with checkpoints as well. I know I didn't put deadline to the checkpoints as opposed to discussion boards, but it's good to catch up while we have the 1 month trial period for the online class. I'm not sure, by the way, if we're going to be extending more than a month because this is under observation as the moment. Okay. So any questions so far before we go to, and welcome to those who just log in into our class. Okay.
I just
And
had a
let me know
question.
if this is working out for you or not, because I can always do asynchronous discussion, meaning I can just record the lesson ahead of time and you can just view it whenever you want. Doesn't have to be this time. But I just wanted to try this because I'm here in case you have questions, especially on the latter lessons.
I just had a question. When was is Module 9? Was that already due, or when is that one?
Yeah, I think it might have been assigned last time. Well, there is no discussion board on module 9, so technically there isn't anything do other than the reading, the checkpoints, and the quizzes. We're
Uh,
way behind our canvas, but we'll probably catch up because we're online, and most of the work will be assigned with currently. Like, for example, we're going to be doing module 12 right now, so I'll be assigning some reading materials in module 12 once we finish our video uh, presentation of the lesson. And it'll be online. So if you have some questions about what you're reading, or you can also read it later. But we'll be assigning current lesson now while we're catching up with past discussion boards. We probably have one or two discussion boards behind at this point, and then we'll be current. Okay, does that answer your question about the
yeah.
module 9? There is no discussion board there, but that's what you're asking. So there's technically no deadline for that one.
All right.
All right. Any other questions before we go to our? Oh, by the way, this is to be announced. Our kind of like, so you could see there, we will be uh, checking it when you're here. Find a way to, if we're extended, then we'll just kind of like have to think about better ways to do this. But for now, don't worry about the packet check. But here are some of the group work that I'm interested in looking at for the packet check. Okay. So good. So go to the next one. All right, so let's do some review. Um, so normally this is part of our warm-up session in class. So we'll just kind of like look at this, and I'll throw in the question to you guys and let me know what you think about it. So let's do a little bit of always, sometimes, and never. Um, first question. The table below is an example of probability distribution. That's a keyword. Oh, I think I can erase that. Okay. Highlighter. So the table below, so this table here. Okay. You guess the highlighter. I don't know. Okay. Yeah, there you go. So this is the table. That's an example of a probability distribution of mutually exclusive events. So take a look at the table and let me know what you think of that. Does anybody remember what is a probability distribution from the class? Or we did auto delete it over the weekends? Okay, so um, one of the properties of or description of probability distribution that we talked about last time is they sum up to 100%. So the breakdown of proportions or percentages, so these part, they have to be 1 or 100%. So for it to be probability distribution. So remember, think we did the roll of dice. Do you remember that in class? We did a pair of dice, and if we kind of like divide all the combinations, so sometimes you get the 1 and a 1, or you get like 2 and a 1, 6 and a 6. Those are rare. So and we ended up kind of like having like a bell-shaped graph out of it. So that's 100% of all the data, and like you chunk it out to different combinations. So if you add all of these, you have 0.3 plus 0.4 plus 0.3 plus 0.2. I think that's about 1.2. So which is more than 100%. So I'll probably pick a never here because it's not considered probability distribution because it's more than 100%. Okay. Any questions about that? Ooh. Good. Let me know if you have some questions. Okay, so let's look at the next one. So this is the next one. Always, sometimes, or never. The shape of the distribution for rolling a fair dice, one piece of dice, is bell shape. Do you think? So only one piece of dice, and it's a fair dice. Just silence the phone. Okay, there you go. So as you know, we have a dice. We have 6 sides, and you know kind of like have each of the side. So each side, it has a 1/6 chance, right? So if they all have the same chance, what kind of distribution, kind of shape would you get for rolling a fair dice?
Uniform, right?
Mm-hmm. Yes, gonna be uniform because they all have a 1/6 chance of getting a 1, a 2, a 3, a 4, a 5, and a 6. They all kind of have the same chance of 1/6. Basically 1/6 type of probability. All right, so because of that, this will also be a never, because this is the wrong part. And just like what you've said, it has to be uniform. Now, if it's 2 dice, like last time, it will be bell shaped because they're not going to be even anymore. Like there's more chance of getting a sum of 7 than a 2, because 2 you can only get from 1 and 1, and 7 you can have a 5 and a 2, 6 and a 1. Does that make sense? So that's not going to be fairly distributed in terms of chances. Okay, cool. Very good. I think that wasn't that bad. Let's go to the next one. Unusual values. So this one is new. Unusual values are beyond, or that means it's either more than or less than 2 standard deviations relative to the mean. So, for example, if I have a symmetric bell-shaped distribution and this is my x bar, that's my mean. So we said that the data spread relative to the center. From the center, it spreads out 1 standard deviation. Okay. Now, if we have 2 standard deviation, so this is -1 standard deviation, and this is now the second standard deviation here. This is the -2 standard deviations, meaning it's lower by 2 standard deviation. What this is saying is unusual values can be found beyond that, meaning here, so that part. Will that be always true, sometimes true, or never true?
Always.
Yeah, that's always true. So these are considered unusual. This is unusually high. Not sure if I misspelled that. And this is unusually low. Remember in our lesson last time, the basketball player who makes a lot of 3 points? Remember that? So it's unusual for him. Yeah. Yes. Curry. So it's unusual for him to score about like I think 10 or 11 3 points in a single game, and also 0 points. Most of his points are concentrated around the middle. So this is always true. Okay. That's very, very far away from the center, because your center is right. Oh, sorry about that. Your center is right there at the middle. Um, so here's your center. So your first standard deviation, which would form the first majority of the data, majority, it's likely to happen that the data will fall right here, okay? Because this is where your average is, your usual. So that's the typical values are here. The bulk, what we call the bulk. So to get into here, it's way too far from the center. So that's not necessarily going to happen, because most of your data or most of your information will be here, because that's where the typical values would be. That's what we call it typical. It's common to be there. Make sense? All right. Okay. So that ends our always, sometimes, never session. A little bit of review of probability distribution. So this is a bit of an empirical approach to it. So we kind of like discuss the difference between empirical probability versus theoretical. Um, and there are 1,000 rolls for the dice, and these are the faces. I know we wanted it to be uniform, because a fair dice supposed to have even even chances for each of the face, but it obviously doesn't look like a fair dice to me. If you kind of like add them, so we can see if it's a probability distribution, because we talked about that the sum of the probabilities has to be equal to 1 or 100%. Okay, so it has to add up to 100%. You okay with that? Pretty sure, if I remember correctly, this should be a probability distribution, but I have a calculator here behind the scene to just double check. I haven't seen this question in a semester. All right, plus 0.141. Yeah, that's exactly 1.00 or 100%. So this is a probability distribution. So this is a yes. Okay, that's, yeah, simple as it is. It may not be a fair die, because as you could see, it's not uniform, but it's it satisfies probability distribution. We're not asking if it's a fair dice. We're asking if it is a probability distribution, or what is a probability distribution. It has to add up all its proportion percentages into 100%. Okay. Cool. Okay. Ooh, let's erase this. Well, I can erase it with the pen. Okay, cool. Let's go to the next one. Again, this one, I think I kind of like spoiled it earlier. So there are two new vocabularies that I want the class to kind of like learn. The first one is typical, which is actually something we've been using from the beginning. And the other one is unusual. So this one is relatively new. This is lifted straight from your canvas. Typical values are those outcomes between one standard deviation below and one standard deviation above the mean. So if you look at the little distribution at the bottom, by the way, this is called the normal distribution. Okay, which is the symmetric version, symmetric bell-shaped distribution. We're now gonna be using normal distribution to kind of like describe it. So it says the typical values will be between one standard deviation above the mean. So this is one standard deviation above the mean. So this is the boundary for that. I might need to mute Cynthia, your background. All right,
Sorry.
so it's all right. But if you want to ask questions, make sure you unmute it. All right, so we have here the typical values. So that's what we call a typical value zone. So this is the portion of your distribution where the data found here will form majority of your data. And we'll find out how much percentage is that in a few minutes. And that's the typical value. And while the unusual values are essentially more than beyond, not more than beyond uh, two standard deviations above or below the mean. So in terms of the graph, where can you find unusual values? They're kind of like here and beyond that. So here, those are unusual. As you could see, even if you look at the graph itself, uh, they're very, very small area that you can find underneath that. Remember, this is a distribution that kind of like gives you also an idea on how big the amount of data is. So this one is very kind of like big type of data. It's what most of the data are. So you could see it's also it has the peak in it. It has a large, big amount of space. Visually, at least, the bigger the space, the more data that it has. So unusual values are going to be found here by the tapers, the end, like the tail side. So these are the unusual values. So good. Um, all right. Let's go to some, before we have some examples. So these are just some definitions for now. And typical values are within one standard deviation, and unusual values are above or below two standard deviations. They're very unlikely to occur if you're just relying on chance. Most of the time, your data will always gonna be here because those are the commonly occurring results. Probability is very high for that to happen. Okay, let's go over. And now, after that little bit of an intro, we go to normal distribution, which is mod 12. Again, this is, by the way, if you came in a little bit late, this is a modified PowerPoint. Don't expect this to last 2 hours. I'm going to be assigning you uh, to go over the rest of, at least the practice quizzes in module 12, so you can read it. You don't have to read it immediately after class. You can read it as long as it's within this week. So we can start doing module 13 after we finish all of module 12. So that's the main difference. We'll spend the rest of the time really going over the modules now, as opposed to homework reading. They'll be part of our online class now. All right, so this is from your handbook. We're still going to be using it as part of instruction. If you want to join me in looking at this, you can make sure you always have your handbook with you. We'll still use it at least for discussion purposes. All right, so first things first, let's take a look at the features of a normal distribution. What is a normal distribution other than it looks like a bell-shaped distribution? Because it is a bell shape, by the way. So normal distribution shape-wise is bell shape. Okay, that's what a normal distribution is. We oftentimes we used to call it symmetric in the past lesson. Um, and some of the other features of a normal distribution is the center is because of the symmetry. If it's a perfectly symmetric type of graph, because of the symmetry, because of the balance, the mirror image balance here at the center. So I'm gonna put the center picture over there. There is a like the left side of that and the right side are perfectly balanced. So you can imagine the center kind of like a crease that if you fold it, like crease on a paper, when you fold it by the center, by the average, that they will kind of like overlap. So the mean is equal to a median because they're perfectly symmetric. That's one of the main feature of that. I'll just highlight that. Both are associated with the peak and divide the area in half. So we kind of like mentioned that earlier. So this half here is the same as the same number of same size as the half here, which in this case is how many percent of the data? How many is it? How many is it? That is a legit question. Well, just like that. All right. That will make up about 50%. Feel free to answer, okay? It's just weird. I know you're there. um, yeah. Feel free to answer the question. All right. So as far as the spread is concerned, um, a measure of spread for a symmetric type of graph, for a bell shape or a normal distribution, we're looking at standard deviation as a way to measure the spread from the center of the distribution. So we mentioned that a while ago that if this is the average, the first standard deviation will actually happen there. And then this is also true for lower than the mean, so below the mean. It will also spread there. Let me just change the color. So that's the first standard deviation. It's the first kind of like one uh, deviation above and below will be how we will measure the spread. One way, at least, to measure the spread, we pair up mean and standard deviation for that. So we did kind of like mention that before, that it's similar to average distance from the mean type of concept. That the more data you have at the center, the lower your standard deviation. The more you have away from the center, the higher the distances, or the higher the mean. It is associated with the inflection point. I'm just reading this just so you know. It is associated with the inflection point on the curve, where the curve transitions from concave up, concave down. Don't have to worry about the word concave up or concave down. So as far as the graph is concerned, concave up is kind of like smiley face portion of the graph. So this one is smiley face portion, well, half of a smiley face. And concave down is like the frown here. You can see there is a frown here on top. So that's the frowning part, and this is also another looking up, concave up type of a portion. So this is concave up and concave down. What this is saying is this point here is a special point where the concave up will become concave down. So the concave up will suddenly become concave down there. This is now becomes concave up again. That's where you can find the first standard deviation. So below the mean and above the mean. Also, we'll kind of like transition into a new type of symbol. We will be using what we call a mu, Greek letter mu. This is pronounced as mu, to signify our mean. Okay, but this is more of the population mean, the whole group. Okay, versus x bar, which we associate as your sample mean. So it's only taken from a smaller group. So if this is your population, if this is the whole group, the sample is just taken there. We'll talk about this more when we hit another chapter. Now the other one is sigma. So this is pronounced sigma. And that is standard deviation of the population. Standard deviation of the population also. So you can now replace this as mu, and then this is basically plus a sigma. This is minus a standard deviation, sigma, over there. All right, so again, just like what I've said, we are switching because we're working on what we call a theoretical model. So, well, here you go. Why is it a special notation? Because we're working with a model, not real data. So we're not using actual samples or X bars. And on the horizontal axis, we labeled the mean as mu. Already show that there. There you go. And one standard deviation below the mean is mu minus sigma. So we subtract their sigma. Well, to be more precise, I guess I should have to put their mu plus sigma. So we add. So if mu is 10 and sigma is 5, then this must be 10 here, and this must be 15, 10 plus 5. And then one standard deviation below is 5. So your typical values will be from 5 to 15, because that's the beginning and end of the first standard deviation above and below the mean. That's where you can find most of the data are. Okay, good. Let me just go to the next one. Let me know if we're moving too fast. You can always go back to this, because I will kind of like record this and upload it. So if you want to go back. There you go. Yes, go. Go ahead.
I just wanted to know if you were going to upload any of these notes, because
Oh, for sure. Yes.
I
You
would.
know where you can find the PowerPoint? It's now renamed as PowerPoint and Video Lessons.
Okay, thank you.
So we're gonna be uploading it there. Let me worry about the mode of upload. I'm gonna save this in my computer so it won't get lost. But thanks for that. Yes, definitely we'll be uploading this, because I don't think everybody's here. We probably are gaining numbers because I'm lagging a little bit now. So I know there's probably more people now. Okay, so let's go to the next one. That's the bell shape graph of that. Okay. Um, let's do some practice. This is good. Been looking forward to this one. So it's best to learn this by actually doing it, isn't it? So this is probably from your to check your understanding part of 125 or 126, one of those two pages. Let's look at the first question. For the normal curve to the right, this one, mark a scale. So we need to mark a scale. Well, there's already tick marks at the bottom of that. On the horizontal axis, so that the mean is 6. So we have a mu of 6 and a sigma of 2. So we did say that this is our mean. So it has to be at the center. So that is a mean of 6. Now, the standard deviation is 2. So we know we are spreading by 2 deviation from the mean. So what will be the first tick mark here? What number will that be?
8.
8, because it's, yeah. So remember, we're spreading by 2. So this is our standard deviation, or our spread from the center. Oh, wrong spelling. Spread from center. And this must be 6 minus 2. This must be a 4. So 8, this will be a 10. This will be a 12. 4 minus 2 is a 2. 2 minus 2 is a 0. So we're only required to actually provide up to the third standard deviation. And there is a reason for that, which we will go over in a bit. So typical values are found on the first standard deviation. So that's our typical values. And the unusual values are found beyond the second standard deviation. So this is the unusual zone. Okay. By the way, this is how we write it. We have a formula for that. So N62, the first number is the mean, and the second number is the standard deviation. And this N means it's a normal distribution. It's a bell-shaped distribution. Okay, so if you see N62, it refers to this graph over here. Make sense? Let's have another example. If you have questions, let me know. Number 2 is working backwards. We do have the normal distribution already available for us. We just need to identify what is the mean and what is the amount of spread from the mean. Okay? So what is the sigma and what is the mu? Our mu here is around 30 because that's the center. And how much is the standard deviation? Anyone?
10.
Yes. There you go. Really easy. So this is an N 30 10. Make sense? So simple as that. Because it's all this, it's gonna be the same shape every single time. All right. Let's go over some other example. Okay, so I guess this is part of the reading material. All right, for every normal distribution, for every normal curve, get my highlighter, the probability that the values, oops, okay, move that thing. The probability that the values lies with 1, 2, or 3 standard deviation from the mean is predictable. So what it's saying is there is an actual percentage. We can know how much data you can find for each of those spread, for the first standard deviation, for the second, and for the third. Well, kind of like spoiler alert, you can see it at the bottom that the first one is around 68.27 here, around 68%. Oh, sorry. I don't know why it does that. If I accidentally double click the thing. Okay. All right. So specifically, the probability that a value is within one standard deviation is around approximately 68%. So typically your value will be part of the 68%. So um, if you're gathering data and it's purely random, 68% essentially is your probability that you can find it within typical values. This is more than 50%. It's more than majority. It's basically majority of your data. So the red zone here, this is your typical zone, your typical values zone. That's around 68%. That's one standard deviation. Now, if you extend all the way to 2 standard deviations, so if you spread from the center all the way to second standard deviation here and there, so 2 standard deviations above and below, that's around 95%. That's almost everything. Only 5% of the data is unaccounted for because they are considered unusual values. That's why they're unusual. There's only 5% chance of them to represent, to show up in your data. Does that make sense? That's why we call them unusual, because 95% of the time you won't find them. If you're just gathering information at random, the chances are you won't necessarily easy to get those data. Um, that's essentially what the 2 standard deviation is. For 3 standard deviations from the mean, so from the center all the way to the third standard deviation. So it's essentially everything here except a very small part of the tail that you don't see anymore. That will make up 99.7% of the data. That is almost all of them, except a very small, narrow taper tail of 0.3%, which is here and there. So maybe about 0.15% there, because it's symmetric, and another 0.15% over there. So it's a very small percentage. That's why we don't represent them anymore. We don't count the fourth standard deviation anymore, because third standard deviation almost account for everything. It's almost everything here. There is, when I was in Manila growing up, I saw this on the news, this documentary where a person has, seemingly like a wood growing out of his hand. I'm not sure if you've seen that. He's like Groot in real life. That's a very rare genetic condition, and it happens to probably less than 10 people around the world. So they're part of beyond the third standard deviation. They're part of the 0.3. That's very rare. Winning a lottery, you're considered more than the third standard deviation because out of millions of people, hundreds of millions of people, only a few of you would win the lottery. So you're not considered part of the within the three standard deviation. You're probably here. And one of the really lucky ones. You're not in the general 99.7%. Okay, so that's what we call the empirical rule of a normal distribution. What is an empirical rule? You might ask. It's the rule that when you start spreading one standard deviation, you're occupying 68% of the graph. Two standard deviation, about 95%. So the first spread, which is one standard deviation, is only 68%. Now, if you spread even further, two standard deviation, you're already occupying 95% of your data. And if you go all the way to the third standard deviation, that's almost everything. It's about 99.7% of the data. That's what we call the empirical rule. So it's 68, 95, 99.7. Okay, might want to memorize that. So 68, 90, 95, 99.7. Any questions on empirical rule? It just tells you how much percent of data can you find between the spread of the data. Okay. All right. Let's go over some more examples. Let's look at this. Weights of a one-year-old boys have normal distribution. Therefore, a normal curve is a good mathematical model for probability distribution, for the probability distribution, which AKA our normal distribution. The mean, the mu, is 22.8 pounds. And the standard deviation, sigma, is 2.2 pounds. Okay, first question. Label the horizontal axis of the normal curve to fit the scenario. So this is our, oops, sorry about that. This is our, which is measured in pounds, our x-axis, which is measured in pounds. Label the horizontal axis. This at the center will be labeled with our mu of 22.8 pounds. And for our first standard deviation, we actually need to add 2.2 following this. Okay. So what will it be?
25.
Yes, so this will be, oh, I cannot write at this size. Okay, I guess we can just write here. So this will be 25. Now this one would be plus 2.2 again, so 27.2. And then this is plus 2.2 again. The third standard deviation above the mean is, what? 29.4. Okay. Then this one will be minus 2.2.
20.6.
20.6. So this will be around 18.4. And minus 2.2. Again, 16.2. Just double check my arithmetic here. I do have a calculator behind the scenes, but it's good to check. So what is the probability? Okay, what percentage from the population, from our distribution, what is the probability that a randomly selected one-year-old boy, so that's our kind of like our population in question, okay, weighs between 20.6 and 25?
68%.
Yes, because it's one standard deviation. So we know that, oh, trying to switch the color of the pen. So we have 20.6 here and 22.8 there. So, 25. That is between 1 sigma, okay? 1 standard deviation. So that is 68%. Because remember, our empirical rule says 68 for the first one, 95% for the second standard deviation spread, 99.7% for the third standard deviation. And next question, what is the probability? I need to get a holder for this tablet because I accidentally touch the Zoom thing all the time. What is the probability that a randomly selected kid weighs more than 25 pounds? So let's think about that. So this time we're looking at more than 25, so it's here. So you did mention earlier that one standard deviation is already 68%. Okay. Ooh. Chose the wrong color there. Oops. All right, so this is already 68%. We know that half of the normal distribution is 50%, right? Because the other half is the other 50%. So it's 50% from here to there. Okay. How much percent is this side of the one standard deviation, and how much percent is this side?
34%.
Yes, good. That should be 34% because it's half of 68%. Half of the 68% is above, and half of them is kind of like below. So that means I'm gonna clear this up for a little bit. Okay. If we are only interested at this portion here, that's basically 34% coming here and half coming there. Agree? So that seems to be, well, everything adds up to 100% as we know, because it's a probability distribution. It's a type of probability distribution. So maybe we can just, what do we do with those numbers?
Subtract them.
Yeah, and subtract them. So 100% minus the percentage that we don't want, which is 84%. Remember, that's 50 and 34. And that will give us the remainder of the highlighted portion, which is about 16%. Double check my arithmetic too, because I'm just kind of like looking at this arithmetically, like just adding those stuffs and subtracting them. All right, okay. Let's look at another example. We're actually close to the end of this discussion. I'll going to be assigning for your reading material. Which probability represents by the shaded area is larger? So what do you think? Which one is a larger percentage? So we have two distributions, A and B. You were given both of their means. They have the same mean. And you were also given how much is the standard deviation. So this is a standard deviation of +1 in here, and this is, you subtract 1. So sigma is 1, and this is a smaller standard deviation. Okay, so which of the two will have a bigger or a larger shaded area, and why? Any guesses? Do you think? Or, are they the same size? Or the taller, the more data that you have? Do you think? So how much percent are the data found here, and how much percent are the data found there? How many standard deviation is the letter A? Because this is your mu. So you have one standard deviation and another one here. So this is the second standard deviation. And how many percent is that in the empirical rule?
95.
95%, yes. So 95% here.
What is
Now, this one, it has the same mean, but it has a smaller standard deviation. So it spreads relatively less.
Yeah.
So it's also second standard deviation, as you could see there. So this should also be 95%. So the answer here is neither one of them is larger than the other. They are of equal proportion, what we call equal proportion or percentages, because they always add up to 100%. What happens is if you make the standard deviation smaller, you will notice that the graph tends to kind of like compress. It's kind of like a balloon, a water balloon. The volume of the water balloon is kind of like 100% of the area of the normal distribution. You can think of it as you can stretch the balloon or you can compress the balloon. It will never change the volume. So now if you try to spread it out further by increasing the standard deviation, you're just stretching it. But then the peak tends to go down. But if you kind of compress it this way, the peak tends to go up because it has to remain 100% at all times. Does that make sense?
Yes.
So we're just kind of like stretching it or compressing it. So you could see the more you actually stretch, the more stretch, the shorter it becomes, and the more compressed, the taller it becomes. It's kind of like it's kind of like a balloon. You cannot change the volume of the balloon. You can just stretch it. It still has the same amount of air or water. Uh, it will just be either stretch version of it or a more compressed version of it. So we're looking at percentages. We're looking at empirical rule to decide, or if it's not within 68, 95, 99.7, we're looking at percentage of it. Okay. Sorry for the bad handwriting. It's hard to write in pen, tablet pen. Okay. Okay. Summary. We have 68, 95, 99.7. 68% of the data is observed to fall within one standard deviation. We have 95% will be definitely two standard deviation. And we have 99.7 of the observations will fall within three standard deviation. Okay. That's the empirical rule. Okay. So 68, 95, 99.7. So typical value, 68%. We don't have really a name for 95%, but I always think of them as like more like, the usual values, but they're not typical. Typical is the most commonly occurring one and the first standard deviation spread. 95 is like usual. You see them, but they're not typical. And then you have beyond the 99.7, that's unusual. So here is the unusual zone in there. So this is unusually high and unusually low here. So very rare type of data can be found there. Okay, so let's go. So IQ scores has a mean of 100 and a standard deviation 15. Use the empirical rule to create a normal distribution. So very easy. So we know that the mean will be at the center, and that is 100. And we'll have to mark the spread up to the third standard deviation. So this will be 115, because that's 100 plus 15 is
100.
mu plus sigma. So we have n 115 here, where this is the mu, this is the sigma. So we add 15, then 130, 115 plus 15 again, and 145. So we keep on adding 15 each time. Any question on that one? Because we're trying to kind of like moving towards a more summary version. So we add 15, we add 15, and we add 15. Which means looking at less than the mean, we have to take away. Remember, that's our standard spread. So it's called the deviation, the standard moving away from the mean, the movement away. So what is this, like 85? Then minus 15 again. What will we get there? Is it like
70.
70? And then minus 15 again
55.
is what?
55.
55, yes. 55. Okay. That's it. So this is the formula. N 115.
What does the N stand for again? The N115?
Oh yeah, the N stands for normal distribution. It's a normal distribution, which is the bell shape that we have here that follows the empirical rule. It has a mean of 100, which is found at the center here. And it spreads by a standard deviation of 15. So this in drawing form is that in distribution form. Okay, any other questions? Or I hope I clarified that. Okay, I think we're almost, oh, there was a question. Let me just erase this. Okay, so Jake has an IQ of 135. Okay, that's a very good number. So Jake has an IQ of 135. Is this considered unusual? So let's look at the normal distribution. Will we consider Jake's IQ unusual for the population whose mean is 100? Jake is 135, so he's around here. So this is where Jake is.
Yes.
Yeah, because we remember unusual values are beyond the second standard deviation. So this is 95%. And Jake is actually outside. So his IQ is unusually high. So he's considered a genius. Oh, they're okay. Unusually high. Because he belongs to the upper 2.5%, because there is also another 2.5% on the other side. So his IQ score ranks on the top 2.5% of the population. That's how we can interpret that. Does that make does that kind of like have a little bit of sense in the unusual thing? Okay, so
Anything over the second standard deviation is unusual.
absolutely. So majority of the population, 95% of the population will have IQ between 70 to 130. So 95% of the people. And there's 2.5% of the population above 130 and 2.5% below 70. Okay. But typically, a typical person will have from 85 to 115 because that's the first standard deviation. Make sense?
Yes.
All right. Oh, let's see. Oh, we're already an hour long. The distribution of Iowa tests of basic skills, vocabulary scores of the 7th grade students in Gary, Indiana is close to normal. Suppose that the distribution is N 6.84155. So this is the mean, and that's the standard deviation. So this is the mu, and this is the sigma. Okay. Okay. What are the other things that is? Oh. Sketch the normal density for this curve. What else? Let me see. Just like, because I already have a thing for that drawn. So this is the normal distribution with all the spread already. Sorry for spoiling it ahead. Just wanted to have another example here because I'm trying to limit the class discussion to around an hour-ish, so you have time to read for the next hour on your own. So what percent of the ITBS vocabulary scores between 3.74, so from here, to 9.94? Oh, very easy. How many percent is that?
95.
95.
Yeah, that's 2 standard deviation. So that's 2 sigmas. Okay, 2 standard deviation. Okay, next, let's see. I hate that when that happens. What percent scores above 5.29? So from here all the way above. So that's the question. What do you think? I think we kind of had the same example last time. It's just backwards.
Oh, it's 84%.
Yeah, that should be 84. Let's break it down. We know that this is 50. This is half. And this is half of 68 because it's half of 1 standard deviation. So that makes up 84%. What percent is below 9.94? So from here all the way down, including the tail. How much is that? Well, more so, how much is this? Because you need to know that to easily answer it as well. So if everything adds up to 100%, maybe we can take away the taper, the tail end. So remember, 95% is 2 standard deviation. How much are the leftovers?
2.5.
5%. So they have to share it. So out of the 5%, 2.5 has to go to the unusually high, and 2.5 has to go to unusually low. Cool. So this must be 2.5 because this is second standard deviation. Okay. So how much is the leftover?
97.
Oh, I mean, yeah, not the leftover, the shaded area. 97.5, right, yeah, correct. So this part here is 97.5. So 100 minus 2.5 will give us 97.5. Okay, good. All right, so those are the two. This is 2.5%. There you go. This is just a quick look. You can actually, they're in the math lab, but you know, you're not supposed to be in the math lab. There are copies of this actually, but I'm including it in our slide. So if you want to go back, check it out. I'm gonna upload this PowerPoint and I'm gonna upload the video, just so you know. Maybe I'll just assign this. I know it's not a group activity, but you can probably try it at home. And maybe we can go ahead and start with this next class. So try page 127. It's exactly the same type of questions. You're supposed to draw and calculate percentages. So that's page 127. So do this for practice, because I want you to have time to go over the module 12 today and not consume, and to limit the file size too. That's another thing. All right. Okay, so let's end it with this. If the IQ score of a student is 135, is this considered unusually high? I think this was Jake. So we answered this as a yes. And what's the main explanation for this?
It's above the standard deviation.
Yeah, it's above, it's beyond 2 standard deviations. So if this is 95%, or this is the second standard deviation from mean, this is considered unusually high. Okay, it's unusually high. Yeah. If it's within 1 standard deviation, 68%, that's the most common thing you'll ever get. That's the typical value. Okay. Expect most of the time it's going to be there. All right, so we'll kind of like end here. For your for continuing with our discussion today, or not really discussion, 'cause, I can stay online, but go ahead to module 12 for some of your readings. So read module 12 and also try those submits or your quizzes. You don't have to finish everything for us today. We'll be working on a weekly basis. So the module 12 uh, discussion boards might have a different deadline, by the way, but the reading material is current. So to reinforce what we've discussed today, because we're not in a regular classroom, we are more animated, we are more flexible in the classroom. I we're it's more informal in the classroom. You can ask me more questions and discussions. So I'll give you opportunity to reinforce this discussion by going to module 12 and working from there. Oops. Okay. Let me just go and click this. Let's see. More.